Hi, in the previous simulation activity, we have already found out the relationship between period time versus different things, or whether or not they are independent of each other. Here, I would like you to deepen your understanding towards simple harmonic motion. In fact, the simulation activity that you did with the spring connected to a mass that go up and down, that is a kind of simple harmonic motion. So the problem is, what exactly is simple harmonic motion? Here, I would like you to read the textbook from the beginning of chapter 4, page 146, all the way keep going until you reach, I think, at least here. Okay, on page 148. So pause the video now and do it.
2,000 years later.
Alright, so let me go through the pages as well and point out the keywords to you. So hopefully you have already found out the same thing. First of all, you have to understand that we are going to talk about several motions, but they are not all simple harmonic motion. In fact, the big family is called periodic motion, and that is not necessarily under the category of simple harmonic motion. So simple harmonic motion, SHM, is a subset, a specific scenario of it. So for example, under the category of human, man is only one subset of it, or a boy, a subset of a man, because boy is like under a certain age of a male that become a boy. So that's the idea itself. So that means if you want to categorize a certain motion into simple harmonic motion, you have to fulfill more requirements. Before we get to this, let's look at what could be periodic motions first. So first of all, whenever you talk about periodic motion, of course, there must be a cycle that repeats itself, and therefore you must be able to measure the time of the cycle. We call it period. Secondly, there must be something moving, and that's called the amplitude. And here is a list of periodic motion that you can go through. And in fact, the pendulum here, it is probably the one of the trickiest. If you're talking about pendulum, of course it is periodic motion, but whether or not it would be treated as simple harmonic motion, it depends on the angle. If the angle is roughly 5 to 10 degree, so that is to say small angle, then we can treat it as simple harmonic motion. The main reason is something to do with the mathematics itself, that if you know small angle approximation, in that case then sine theta will be approximately equal to theta in radian. Then in this case we can mathematically prove that it is simple harmonic motion. However, if the angle is bigger than the so-called small angle, which is maybe greater than 10 degree, then you should not be treating it as simple harmonic motion. You can only treat it as periodic motion. And so here are the list of what could be oscillating. So of course, the spring that we did earlier in the simulation, it could be simply a rounded bottom ball with a ball that is rolling, a bit similar to the PhED simulation, which is this one, right? So imagine this is the ball and this is the ball, and then this is kind of oscillating. I mean, it is oscillating from one to another. However, this is not simple harmonic motion, and it will explain later on. Next will be the vertical motion of a body floating in the liquid under the action of wind and waves. So like iceberg. I think what it's describing is more like I'm not showing the wind or waves, but then if you simply think about this going up and down, this is kind of an oscillation as well, right? When you simply drop something vertically into the liquid. The next thing could be any kind of string instrument that you play. Could be a guitar, could be a violin, etc. And of course, you know when they are making a sound, then it's because of their vibration, and vibration itself is a periodic motion. And that is similar to the diving board. When someone jump from it, then it will also oscillate, as well as the airplane's wing, because if you think about, there is a wind that's going to the airfoil, then it actually will also oscillate as well under the strong wind or thunderstorm. So these you can imagine, I mean, I can't find a proper video on that, but then you can also take it as, or simply model as a ruler that you plug it and then it will oscillate as well. And lastly, it could be the tree or skyscraper that is, you know, vibrating under the action of wind. So notice that these are just examples of oscillations. They are not necessarily the simple harmonic motion. So now we'll go into the definition of simple harmonic motion. So first of all, in order to have simple harmonic motion, we must have the magnitude of the acceleration proportional to the displacement from the equilibrium. And that's the first thing. Second thing is the direction of the acceleration is always towards the equilibrium position. So mathematically, we could simply express it as A proportional to negative x. And if you try to double check this idea with the simulation activity that we did with the spring mass system, which you can see in the picture below, this is horizontal, however, but then if you try to think about the vertical one that we did, it's also the same. So for example, this is a block with the equilibrium position, and now you try to pull it a bit more to let it release and, you know, start to oscillate. And at this instant already, but by the moment you release it, you can already see the acceleration is going to go up, right? Because the equilibrium point is here, right? And then you are going up, but then the displacement from the equilibrium position is going down like this, right? Starting from here exactly and all the way to the mass here. And if you try to think about whether or not they are proportional and always in the opposite direction, this can be derived using the simple equation that is F equals to ma, right? This is how we can determine the acceleration. At the same time, the only force that we have, I mean, in fact, there is weight, but then if you go back and look at the last section of our simulation activity, we know that weight has been cancelled out for some reason. So the only force that is effective would be the tension, and that's negative kx, x being the displacement. And so that should equal to ma, and you can see that x and a will be having a negative proportional relationship.
Negative proportional relationship.
Wait, did I say negative proportional relationship? No, that's not right. I mean, if you refer to negative proportional, or more normally people call it inverse relationship, that is like a graph like this, but this is not what we want. We should, however, more precisely say A is proportional to negative x, okay, not negative proportional, proportional to negative x, because the graph that we have eventually will be something like this one, okay, which of course pass through origin, and then a, yeah, like I said, a proportional to negative x. But then if you look at the so-called inverse relationship, that's not the same equation, right? That's y equal to 1 over x, so don't mix it up. And because of this simple, elegant mathematical relationship that a is proportional to negative x, then we can also have some characteristic find out from the simple harmonic motion. That's the same result as what you find out in the simulation activity earlier. So let's just go through them again. So first of all, you should find the period is always the same, no matter how many cycles that you have done. The time for one period is always the same, and that's the same for the amplitude as well. So it's always maintained constant for simple harmonic motion. Here again, we are talking about there's no friction involved. Next, the period is independent of the amplitude. So that's the last test that you find out. No matter how much you pull from the equilibrium, the period is always the same. So that's why if you, last video I talked about the astronaut in the space station. They use the spring to actually measure the mass of their own body. And lastly, the displacement, velocity, and acceleration time graph. Okay, we are talking about time graph are always sine or cosine. So if you want to see how it looks like, it's actually right here. Okay, so if x looks like this, then v would look like this. All right, and then if you are good at differentiation, then of course you know again v equals to dx over dt, and then you will be able to see the differentiation of sine x with respect to sine t with respect to t will become cosine simply. So that's how it can be transformed from one to another. If you are not good at differentiation, that's also fine as well. You won't be asking in IB physics, but then at least I hope what you can see is when x is at maximum, velocity is at 0, and that's something to do with like the simulation that you have done earlier. Think about when, say, this is the equilibrium, when the spring is extended the most. This is the turning point, right? This is when you try to go back up, and then when you reach the other end, like the maximum displacement, which is the amplitude, then again velocity at that time would be 0, but then x would be maximum. Similarly, when you pass through the equilibrium point, that means when x is at 0, then the velocity, the corresponding time, velocity will be at maximum in magnitude. Here will be of course the negative maximum, but then in terms of magnitude it's just maximum. Same as the other way around, when you pass through the equilibrium point again, the velocity will also be maximum again. So this is the relationship between x and velocity. Alright, in case you don't understand still, you can go back to try to look at the simulation. So here I enabled velocity, acceleration. For displacement, you can judge it on your own simply. So say at this point, right, this is when velocity is the maximum. Acceleration will be 0 because x displacement is also 0. They are proportional to each other's negative, and so when one is 0, the other one is negative 0, which is also 0. Okay, so this is the instant that I was talking about, and you can also see when you reach the highest one just now, like earlier, as I said earlier, the velocity was at a moment, at a short instant, become 0 when the displacement is at maximum, and also the acceleration at maximum as well. And this continue again just now when it passed through the middle, the acceleration is 0 and velocity is maximum. And when you reach to the bottom, just now velocity becomes 0 at that again very short instant, and acceleration is maximum. And you can see acceleration, like we said, is always pointing towards the equilibrium. So that's why now it's up, always up, now it's always down. Alright, because the equilibrium is in the middle. And so here is a very, very important and nice graph that you can see. Okay, so displacement, acceleration, and velocity. So the first thing that I would like you to see is try to compare x and a acceleration. And again, you should find they are having proportional to the negative of each other. So that's why when displacement is red, right? Yeah, okay, so red, and the acceleration is here, purple, and you can see displacement is at maximum, although it's kind of small value, but that is already maximum. Here is also maximum, but then they are opposite to each other. So one is positive maximum, one is negative maximum. Same as later on. Now acceleration is positive maximum and displacement is negative maximum. Okay, and so these are all the extreme point that I can show you. Similarly, you can also see, like what we said earlier, that displacement and velocity, there is always a lagging. So when one is maximum, the other one is 0. Maximum 0, maximum 0, maximum 0, maximum 0, etc. The following is a very important idea, however, it may be slightly more challenging to some of you, so please bear with me. I would like to introduce you an idea called phase difference. And this is when we talk about between two periodic motion with the same period, then they may not be exactly synchronized. So for example, there are two situations where it's like the most extreme. We call it in phase, and the second one is called out of phase. Okay, and so imagine my hand here is two springs. If they go up and down together, like you and your best friend, then you guys are in phase. Okay, you are synchronized in phase. And if you and your worst enemy, you always do the opposite thing, right? And you guys are out of phase. So that is like when you do like this, right? When one go up, the other one go down, then that means this is out of phase. So if I try to use the simulation to hopefully to show you that we can set like something like this, maybe. Okay, so this, okay, you can see it going up and down at the same time, then they are in phase in terms of their whatever their displacement, their velocity, and their acceleration to each other, they are always in phase. Or I can set it like maybe like this, then they will always be out of phase. Yeah, one go up, one go down, so they are always out of phase. Yeah, it's very satisfying to see this. However, there are times where the things, they are oscillating, but they are not exactly in phase or out of phase. They may be lagged by a certain degree of time. So back to this graph. Again, this is a super nice graph that describes SHM. And we have acceleration, velocity, and displacement. If you try to pick a certain point for comparison, for example, the peak of acceleration, the peak of velocity, and the peak of displacement, you can see that it's always lagging from acceleration, or leading, I should say, acceleration leading the velocity, velocity leading the displacement by a certain phase difference. All right, and for phase difference, we'll describe it with degree or radian, because if you think about it, the whole cycle is like a circle of life, and a circle is 360 degree or 2 pi. Okay, in radian. And so what you have to do simply is thinking about like how long it is for one cycle. And so here you have about 2 seconds, right? 1 and 3, so 2 seconds is one period. And if you look at this one and this one, this is 0.5, this is also 0.5. Okay, and so 0.5 over 2 is a quarter, and a quarter out of 360 degree is 90 degree. Okay, so that means you can say acceleration is leading velocity with 90 degree, or velocity is leading displacement with 90 degree. This is the phase difference that we're talking about. In radian, then that will be 2 pi over 4. That means it is pi over 2 instead of 90 degree. You can also apply the same idea to quantify the so-called idea of in phase and out of phase. So in phase is simply they move together, so obviously the phase difference would be simply 0 degree. For out of phase, then that would be 180 degree, or you can call it pi. Simply pi is 180 degree. And here is one more example for you. The textbook gave you, there are just simply 3 examples of simple harmonic motions, and first of all they are having the same period, and this is something that you have to understand. Like when you try to compare the phase difference, the period has to be the same. If they are not having the same period, then nothing you can talk about, because their phase difference is always changing, so that's no point to talk about that. So the one that we talked about earlier was one object and its acceleration, velocity, and displacement, but here it's just an example, so don't mix them up. So just having 3 random objects and this is their motion, and so the problem is, how do we find out their phase difference? So once again, the first thing that you have to do is to find out the cycle time, that means the period. So from here to here, you find it is 1 second in total. And if you try to pick a point and try to find out the time difference between them, from red to blue, blue to purple, I think this is 0.5, and so this is about the half, so this should be 0.25, and this is also half of it, so this should be 0.125, right? And so this is obviously 0, the origin. So if you try to calculate how much the red one is leading the blue, that is obviously 0.125, divide the whole cycle, 1 or 1.00 if you like to, and that should be 1/8. Okay, and 360 degree of 1/8 would be 45 degree, or you can use pi over 4 radian. And that's the same, of course, for blue to purple, but then you can also compare red to purple as well. And obviously this is 45 degree and 45 degree altogether, that means 90 degree if you are talking about red to purple. Okay, so here you have it. In this video you have learned about the idea of oscillation first of all, and you should know that simple harmonic motion is a subset of oscillation or periodic motion. And some examples of periodic motion including the pendulum, when it is small angle then it is SHM. And you have also learned about the characteristic, very interesting characteristic of SHM. And lastly, you have also find out the phase difference between the acceleration, velocity, and displacement in simple harmonic motion, and not to mention, of course, the idea of phase difference itself. I hope you enjoy learning physics with me. If you do so, please hit the like button now and subscribe to my channel. In the next video, we'll try to do some practice. See you in the next video. Bye.